Under the desolate desert sky, as the night of December 26th bled into the 27th, 1944, a silent vigil unfolded. Deep within the sprawling, clandestine Hanford site, nestled in the vast, remote expanse of Washington state, a colossal concrete canyon stretched over 800 feet. Inside its formidable embrace, operators stood sentinel. Shielded by immense barriers of lead and steel, they bore witness to an eye. This was no ordinary factory churning out steel, gasoline, or conventional explosives. Their singular quest was to harvest something so inconceivably rare, so infinitesimally present, that within the fiercely radioactive uranium emerging from Hanford's reactors, only one atom in every 4,000 had undergone the miraculous transformation into plutonium. Here lay the profound paradox. For one of the Second World War's most critical manufacturing endeavors, the engineers deliberately bypassed the theoretically strongest, most elegant chemical pathways. They embraced a process less refined on paper, less efficient than future methods, one designed for a plant that would become almost lethally inaccessible during its blistering radioactive operations. The imperative was survival. At Hanford's tea plant in 1944, the winning solution was not the most scientifically pristine. It was the one forged in the crucible of extreme conditions, capable of enduring immense scale, relentless speed, overwhelming radiation, and the absolute necessity of remote manipulation, all at once. Tonight, we delve into the precise calculus behind tea plants' reliance on bismuth phosphate. We will uncover the intricate mechanics of this chemistry, illuminate why alternative methods proved unsuitable for the colossal demands of wartime production, and reveal how this gargantuan factory stood as an audacious engineering answer to one brutal, existential question. How does one isolate a microscopic quantity of plutonium from an overwhelming mass of uranium and a chaotic, deadly cocktail of fission byproducts, when such an feat has never been attempted on this scale by human hands? The true epiphany arrived when the engineers abandoned the pursuit of laboratory perfection. They ceased asking what could be ideal in a sterile beaker, and instead confronted the stark reality. What would still function within the searing heart of a radioactive canyon? To grasp the profound wisdom of their choice, we must first broaden our perspective. By late 1944, the brilliant minds of the Manhattan Project had conquered but one formidable hurdle in the plutonium saga at Hanford. The colossal reactors had proven their terrifying capability to forge plutonium through the intense irradiation of uranium fuel slugs. At the pioneering B reactor, soon joined by its formidable siblings, D and F, uranium elements rested within the reactor's core, bathed in a torrent of neutrons. For precisely the right duration, atoms absorbed these particles, undergoing an alchemical transformation, birthing the coveted new element. This initial triumph, however revolutionary, immediately spawned a second, even more intractable problem. Once extracted, the irradiated fuel slugs were not merely hot, they were intensely, lethally radioactive. They posed an extreme chemical hazard, a profound radiological threat, rendering them almost impossible to handle safely. And the precious plutonium, the very essence of their mission, lay inextricably entangled within this deadly matrix, mingled with residual uranium, a bewildering array of fission products, and a chaotic, incandescent soup of radioactive byproducts. Therefore, the true mission transcended merely creating plutonium. It demanded its perilous, meticulous extraction. The challenge was not just to make the impossible, but to then snatch it from the jaws of absolute destruction. An ambition of unprecedented scale demanded an industrial-grade chemical separation, ATID 221T, within the sprawling, secretive Hanford engineer, Works 200 West area. Workers, gazing upon these colossal structures, bestowed upon them the evocative nickname Queen Mary's, a testament to their immense length and cavernous interiors, echoing the grandeur of the era's great ocean liners, yet concealing a far more perilous cargo. The sheer architecture of the tea plant itself was a stark declaration of the extreme challenges it was built to overcome. This monumental edifice stretched roughly 800 feet long, 65 feet wide, and soared 80 feet into the air. Imagine a structure nearly 3 football fields laid end to end, its height comparable to an 8-story building, all dedicated to an invisible, deadly alchemy. Within its concrete shell, a formidable array of massive cells lined the interior. Many of these formidable chambers measured approximately 15 feet square and plunged 20 feet deep, each a fortified vault designed to contain the unimaginable. These cells were separated by 6-foot-thick concrete walls, formidable barriers against an unseen enemy. Their tops were sealed by removable concrete blocks, each around 6 feet thick, some weighing an astounding 35 tons. This was not the pragmatic design of ordinary chemistry. This was the architecture of an entirely new, fearsome science, where human presence near the equipment during hot operations was a guarantee of swift, agonizing death. Operators, therefore, were relegated to separate galleries, a profound physical and psychological distance from the processes they controlled. One dedicated level hummed with the intricate web of electrical controls, a nervous system of power and precision. Another gallery managed the complex network of piping and remote lubrication systems, ensuring the monstrous machinery ran without direct human touch. High above these, the central control area offered a precarious vantage point. Here, a cadre of engineers and technicians peered through periscopes, manipulated an array of remote controls, and deciphered the grainy images transmitted by early closed-circuit television, all to monitor the volatile processes unfolding behind impenetrable shielding. The tea plant was a paradox, a chemical factory, a fortress, and a remote command center fused into a single, terrifying entity. Yet despite the monumental effort invested in its construction, the builders could not have fully grasped that the very scale of this edifice would render the choice of chemical process even more critical than the building itself, for it is in the perilous chasm between a laboratory experiment and a full-scale radioactive production plant that countless brilliant ideas meet their demise. The initial question seemed deceptively straightforward. If chemists had already devised methods to separate plutonium in the laboratory, why not simply amplify the most promising one? The answer lay in a brutal truth. Wartime chemistry does not confine itself to the pristine pages of a scientific journal or the sanitized confines of a beaker. It manifests in the unforgiving reality of industrial components, in the relentless wear on pipes, the integrity of tanks, the reliability of valves, the resilience of seals, the unforgiving demands of maintenance schedules, the insidious creep of corrosion rates, and the myriad potential points of catastrophic failure. In the pivotal year of 1944, the Manhattan Project found itself ensnared by at least 4 simultaneous, severe constraints, each threatening to derail the entire undertaking. First among these was the crushing imperative of speed. General Leslie Groves, the project's formidable director, and the entire Manhattan Project leadership understood they simply did not possess the luxury of years to meticulously refine a perfect process. The production plant had to be operational on a wartime timetable, a schedule dictated by the relentless ticking clock of global conflict. What was needed was something dependable, something that could be brought online with unprecedented haste, even if it represented a pragmatic compromise rather than the ultimate, long-term solution. The second, and perhaps most terrifying constraint, was radiation. This was no sterile academic laboratory, where experiments could be meticulously controlled and safely contained. Once the irradiated fuel slugs were dissolved, the entire liquid stream transformed into an intensely radioactive hazard, demanding an entirely new paradigm of remote handling. Workers could not simply stroll in to replace a faulty valve, clear a blocked line, or perform routine maintenance with conventional tools and procedures. The invisible, deadly emanations meant every single interaction had to be mediated, manipulated from a distance, or risked fatal exposure. The very nature of the chosen process for the tea plant had to contend with a terrifying reality. Direct human access would become an impossibility once full radioactive operations commenced. Every design, every chemical reaction, every piece of equipment had to function flawlessly within an environment utterly hostile to life. Beyond the specter of radiation, the project faced a monumental leap in scale. Glenn Seaborg's groundbreaking chemistry, which had unlocked the secrets of plutonium, had been meticulously developed using microscopic, almost immeasurable amounts of the element within the pristine confines of a laboratory. The tea plant, however, demanded something radically different. It would manipulate roughly 1 billion times more chemicals than those initial, delicate experiments. This colossal jump transformed every parameter. What were once negligible impurities in a beaker became catastrophic blockages or contaminants across vast industrial systems. The subtle nuances of how fluids behaved under pressure, the relentless grind of corrosion against metal, the absolute necessity of unwavering reliability. These were not mere engineering considerations. They were existential threats to the entire endeavor. Then came the agonizing choice of materials. One prominent alternative process, initially promising, relied on lanthanum fluoride. In certain respects, it offered superior plutonium carryover, a tantalizing efficiency. Yet, this method was inextricably linked to hydrofluoric acid, a chemical notorious as one of the most savagely corrosive substances known to industrial science. In any conventional plant, the threat of corrosion is a constant, dangerous adversary. But within the remote, shielded canyons of the tea plant, corrosion transcended mere danger. It became a strategic vulnerability of the highest order. Imagine the horror: hydrofluoric acid, unleashed, gnawing through critical equipment deep inside those heavily shielded cells. The entire production chain, a linchpin of wartime necessity, could slow to a crawl, or worse, fail completely. And this failure would occur in a place where maintenance was not merely difficult or dangerous, but rendered almost impossible, heavily constrained by lethal levels of radiation. This stark reality underscored the profound difficulty of the decision. The chemists and engineers were not merely asking which method could separate plutonium most effectively in a theoretical vacuum. Their question was far more brutal, far more urgent. Which method possessed the sheer resilience to survive industrial-scale demands, remote handling, the breakneck pace of wartime construction, the relentless assault of radiation, and the unforgiving pressure of an existential deadline? Ultimately, Crawford Greenwald of DuPont made the definitive choice, selecting bismuth phosphate for the main separation stages. Even Seaborg himself would later concede that, at first glance, there wasn't always a dramatic, obvious difference between the competing contenders. Yet one issue stood out with chilling clarity. The fluoride-based processes, with their inescapable reliance on hydrofluoric acid, made them profoundly less attractive for the massive, high-volume production stages demanded by the project. It sounds almost anticlimactic, a decision devoid of dramatic scientific breakthroughs or fantastical machines. No magical catalyst, no miraculous shortcut. Just a hard-nosed, unyielding engineering judgment. Employ the chemistry that the PL avoiding the worst corrosion risk, however, was only half the battle. The greatest challenge still loomed. The chosen process still had to achieve the seemingly impossible, separating an almost imperceptible amount of plutonium from a gargantuan mass of other material, step by painstaking step, deep within those remote concrete cells. And it was here, in this crucible of practical necessity, that bismuth phosphate revealed its true brilliance. To grasp its ingenious simplicity, imagine a scenario. You have spilled a minuscule quantity of shimmering glitter into a truckload of wet sand. Attempting to pick out each individual grain of glitter would be an exercise in futility, an impossible task. Instead, the bismuth phosphate method introduced something that the glitter, the precious plutonium, inherently desired to cling to. This new substance would then form a distinct clump, which could be easily and reliably pulled away from the overwhelming bulk of the surrounding material. This elegant, practical solution, born of necessity, was the key to unlocking the power hidden within the atom. At the very heart of the bismuth phosphate process lay an elegant, almost deceptive logic. Its entire ingenuity hinged upon plutonium's elusive chemical state, what scientists precisely define as its valence. Imagine a substance with two distinct personalities, each dictating its fate within a liquid world. In one specific state, plutonium would become an inseparable companion, clinging to the bismuth phosphate as it solidified and precipitated out of solution. Yet, shift its valence, alter its very identity, and plutonium would remain suspended, aloof, while the bismuth phosphate crystals descended, leaving it behind. This fundamental dichotomy offered engineers an unprecedented degree of manipulation. They could, with precise chemical intervention, coerce plutonium to switch between these states at will. They could force it to either join the solid mass and be carried away, or to patiently linger in the liquid, awaiting its next transformation. This cycle, repeated with meticulous precision, became the engine of refinement, stripping away unwanted material, one microscopic layer at a time. It was a relentless, calculated dance of separation. The process, at its operational core, unfolded in a series of dramatic steps. First, the protective aluminum cladding encasing the nuclear fuel rods had to be carefully removed. This exposed the raw uranium, which was then dissolved, creating a solution of immense, unseen radioactivity. This was a liquid cauldron of raw, untamed power, a silent testament to the destructive potential harnessed within. Next, a precise cocktail of chemicals was introduced, triggering the formation of bismuth phosphate as a dense, solid precipitate. Here, the critical manipulation occurred. With plutonium held in its +4 valence state, it would bind itself inextricably to this descending precipitate, becoming a captive passenger on its journey to the bottom. The mixture could then be separated. The solid, now laden with plutonium, would be siphoned off for further processing, while the vast majority of the lethal waste remained trapped within the liquid, isolated. But the journey was far from over. Chemists then meticulously shifted the plutonium into a different state, typically the +6 valence. This crucial change meant plutoneration. The cycle continued, dissolving, separating, refining. It was, in essence, a chemical sleight of hand, forcing plutonium to repeatedly switch allegiances, joining the solid, then remaining in the liquid, then rejoining the solid, then staying in the liquid once more. This repetition was not a sign of inefficiency. It was the very essence of the strategy. The bismuth phosphate process was a batch precipitation system, not a single, elegant pass. But batch systems, with their iterative nature, possess an extraordinary power when the ultimate goal is absolute control, staged purification, and an unwavering, dependable operation. At the T plant, this relentless sequence of stages dramatically reduced the radioactivity to levels previously unimaginable. The initial extraction step alone slashed gamma activity by a factor of roughly 10. Subsequent decontamination stages then reduced it by an astonishing factor of approximately 10,000. This cumulative effort resulted in an overall decontamination factor of around 100,000 times less than the original uranium solution. Such a profound reduction was not merely a technical achievement, it was a fundamental necessity. The objective transcended simple separation. It was about forging a product stream so meticulously purified that it could be safely handled in subsequent processing steps, under far greater control, shielding human hands from the invisible, deadly energies. Yet even within this ingenious system, there were layers of refinement. Bismuth phosphate, while indispensable for the high-volume initial stages, was not a universal solution. For the critical, later, crossover stages, where purity demands reached their zenith and volumes were significantly smaller, Hanford engineers turned to another compound, lanthanum fluoride. This strategic shift underscored the relentless pursuit of perfection, adapting the chemical tools to the escalating demands of an unprecedented task. Each step a testament to human ingenuity, confronting the formidable power of the atom. The very nature of its existence demanded a nuanced approach. This alternative method proved indispensable, capable of extracting specific fission products that the primary bismuth route, for all its robustness, simply could not handle with the same exacting efficiency. This reveals a profound truth about the minds at work. These were not engineers bound by dogma, nor were they practitioners of a single, universal solution. Their methodology was one of precise adaptation. They understood that each challenge within this colossal undertaking required a bespoke answer. For the vast, unforgiving environments of industrial-scale separation, the sturdy bismuth phosphate process was the chosen titan. Yet, when the volumes became smaller, when the need for delicate precision outweighed the sheer brute force of the main stages, lanthanum fluoride emerged as the indispensable tool. Its inherent strengths, coupled with its more manageable hazards in contained settings, made it the ideal candidate. This was not a reluctant compromise. It was the epitome of intelligent systems engineering, a testament to strategic foresight under unimaginable pressure. But the elegant equations and meticulous laboratory procedures were merely the overture. A chemical process, however brilliant on a flow sheet, still had to be forged into a tangible reality. The T plant, a gargantuan fortress of concrete and steel, stood as the ultimate test, a facility designed to wrestle with the invisible, deadly forces of radiation on an unprecedented scale. Before a single irradiated fuel slug ever entered its labyrinthine chambers, the chosen chemistry had to undergo its own crucible of fire. Crucial developmental work unfolded across the vast network of the Manhattan Project's chemistry efforts, from the intellectual hub of the Metallurgical Laboratory in Chicago to the semi-works facilities nestled within the secret city of Oak Ridge. These pilot and semi-pilot operations were more than mere experiments. They were vital proving grounds, meticulously demonstrating that the bismuth phosphate route could indeed carry plutonium with the necessary efficacy for industrial-scale production. By late 1942, the decision-makers, acutely aware of the ticking clock, gravitated toward a precipitation process. It offered the greatest certainty of success within the impossibly tight time frame. Then, on May 31st, 1943, the bismuth phosphate process received its official sanction for the main production stages. The theoretical had been accepted. Now came the terrifying leap into the practical. Scale up. Across the desolate, windswept plains of Hanford, thousands of hands began the monumental task of constructing the T-separation plant in 1943. This was an undertaking plagued by the relentless realities of wartime. Labor shortages were endemic. Blueprints often arrived unfinished or underwent constant revision, and competing national priorities vied for every scarce resource. The entire endeavor was steeped in the general chaos and furious expansion of a nation at war. Yet with a pace that defied all reason, by December 1944, the T-plant stood complete, ready to receive its deadly cargo. Consider the sheer audacity of that timeline. A plutonium separation canyon, the first of its kind anywhere on Earth, conceived and constructed in roughly 18 months. This architectural marvel, built under the crushing weight of wartime urgency, was designed to implement a process no human had ever attempted on such a scale. Inside this fortress, every design principle revolved around three imperatives: controlled flow, impenetrable shielding, and absolute distance. Irradiated fuel slugs, having undergone a critical cooling period submerged in water after their time in the reactors, represented the most hazardous material on the planet. Workers, shielded by layers of lead and concrete, employed incredibly long handling tools and specialized transport methods to guide these glowing cylinders into water-filled casks mounted on rail cars. These rail cars, moving with deliberate slowness, carried their precious, perilous cargo towards the heart of the separation area. Once inside the T-plant, the fuel began its journey through a sequence of towering concrete cells. Within these heavily shielded compartments, the intricate ballet of dissolution, precipitation, separation, and decontamination unfolded in precise, sequential stages. Direct human access during these hot operations was not merely limited, it was impossible. Every aspect of the plant, therefore, had to be meticulously engineered for remote observation, remote control, and perhaps most critically, remote maintenance. It was a silent, unseen choreography of machinery, guided by human minds, yet never touched by human hands. The entire operation was a masterclass in ingenuity born of necessity, a testament to the fact that even the most abstract scientific principles could be transformed into an industrial reality, defying every known limitation, all to serve a singular, urgent purpose. This was where the true, unvarnished value of bismuth phosphate illuminated itself, stark and undeniable. This was a process engineered to circumvent the most relentlessly corrosive chemical pathways, a design imperative born from the brutal reality of the T-plant itself. Within its colossal, concrete-shrouded walls, deep in the heart of the Hanford site, any breach, any structural compromise, was not merely a maintenance headache. It represented an existential threat to the entire project. This was no ordinary industrial facility where a faulty valve or a corroded pipe could be casually accessed, repaired, or replaced. The T-plant was a fortress of radioactive materials, a sealed environment where human intervention was all but impossible, a monument to remote operation where every decision, every design choice, carried the weight of catastrophic failure. In a conventional chemical plant, engineers might tolerate a higher frequency of maintenance issues in exchange for marginally superior chemical performance. It was a calculated risk, a balance struck in the pursuit of efficiency. But at the tea plant, the stakes were impossibly high. Maintenance trouble here meant a catastrophic halt to production, an agonizing delay in the race against time, a potential unraveling of the entire strategic imperative. And then, the ultimate test arrived, the moment of truth. Historical records, meticulously preserved, reveal the silent, unseen drama that unfolded. The very first batch of fully irradiated fuel rods, carefully extracted from the mighty B reactor and pushed through its channels in late November, began its perilous journey. It was processed through the intricate, unseen labyrinth of the tea plant during the hushed hours of the night, between December 26th and December 27th, 1944. A silent, chemical ballet performed under the shadow of a global conflict while the world celebrated or mourned the holiday season. Yet the tea plant was but one critical stage in a multi-layered, unforgiving sequence. After its initial processing, the precious, nascent material continued its clandestine passage. It moved through the 224T bulk reduction building, where its volume was drastically reduced, and then into the 231W isolation building. Here, the product was further concentrated, refined, and meticulously converted into a more stable, manageable plutonium nitrate paste, ready for its final, crucial shipment. On February 2nd, 1945, a date etched into the annals of history, the first separated plutonium nitrate paste from Hanford was dispatched, a silent harbinger of immense power, bound for the secretive laboratories of Los Alamos. When the question inevitably arises, why bismuth phosphate? The answer transcends mere theoretical elegance. The profound truth lies not just in its conceptual viability, but in its unparalleled, demonstrated efficacy across the entire, unforgiving chain of operations. From the moment the fuel rods were discharged from the reactor, through the cooling process, the hazardous transport, the remote canyon chemistry, the intricate concentration, and finally, to the preparation for shipment, bismuth phosphate proved its mettle. It was a solution that didn't just work on paper, it worked in the crucible of reality. This, then, is the fundamental distinction between a promising chemical idea and an indispensable industrial solution. The former might capture the imagination, the latter changes the course of history. Now, the central question can be addressed with absolute clarity. Why did Hanford's tea plant rely on bismuth phosphate in 1944? Because the conventional notion of the best method, judged purely by isolated chemical metrics, was utterly the wrong standard for that desperate hour. If one were to evaluate solely by a singular chemical measure, other approaches might indeed appear more appealing at certain stages, and if the judgment were based on long-term industrial evolution, later, more sophisticated processes, such as redox and subsequently purex, would undeniably surpass bismuth phosphate. Those advanced methods offered the dual recovery of both plutonium and uranium, employing more sophisticated solvent extraction systems, ushering in a new era of efficiency. But the tea plant's challenge was not a 1950s optimization problem. It was a 1944 wartime startup problem, an urgent existential race against time. The plant demanded a method that was swift enough to deploy with minimal delay, reliable enough to scale to unprecedented industrial levels, tough enough to withstand the rigors of remote, unseen operation, and practical enough to mitigate the colossal corrosion risks inherent in its primary production stages. It needed to be simple enough to run in batch form within those massive shielded cells, and perhaps most critically, proven enough to instill unwavering confidence in the war leaders whose decisions carried the fate of nations. Bismuth phosphate, in that singular defining moment, met that precise multifaceted combination of demands with an unmatched superiority over every available alternative. It was not merely a chemical, it was the key to unlocking an atomic age, forged in the crucible of necessity. It was a crucible of necessity, forged in the relentless fires of global conflict. The process, for all its revolutionary output, was far from elegant. Later systems would achieve a cleaner alchemy, capable of recovering precious uranium for reuse. This method, however, did not. Instead, it generated a torrent of caustic byproducts and highly active residues, an environmental burden of staggering proportions. Its operation demanded a laborious sequence of discrete stages, a stark contrast to the fluid, continuous processes that engineers dreamed of. These were not unforeseen flaws. They were accepted costs. They were the unavoidable tolls levied by a wartime program, desperate for one elusive commodity: certainty. This fundamental truth often escapes those who chronicle the annals of engineering history. They see only the imperfections, missing the profound context of a world teetering on the brink. Great wartime engineering rarely champions the most theoretically advanced concept. Its true genius lies in the pragmatic selection of an idea that offers the optimal balance. Speed was paramount, measured in weeks and days, not years. Robustness was non-negotiable, demanding systems that could withstand immense pressure and relentless operation. Manufacturability meant designs that could be scaled from laboratory bench to industrial behemoth with unprecedented velocity. A generous safety margin was essential, acknowledging the unknown perils of a nascent technology. And, critically, operational realism dictated methods that could be executed by thousands of workers, many with limited specialized training, under conditions of extreme urgency and secrecy. The very chemistry employed within the tea plant was not merely a scientific discovery. It was a design decision, a calculated gamble shaped as much by the unforgiving realities of industrial valves, the impenetrable embrace of concrete shielding, the crushing weight of deadlines, and the stringent limits on repair access, as it was by the delicate dance of molecules in a test tube. The true breakthrough arrived when the Manhattan Project dared to reimagine chemistry itself. It ceased to be an isolated laboratory science, a realm of pristine beakers and theoretical purity. It was transformed, brutally and brilliantly, into factory design, an integral component of a vast, complex industrial enterprise. In the immediate term, the tea plant delivered an undeniable triumph, proving that industrial-scale plutonium separation was not merely a theoretical possibility, but an achievable, tangible reality. This singular accomplishment etched its name into history. It stood as the world's first large-scale facility dedicated to the separation of plutonium, a monument to human ingenuity under duress. It bridged the chasm between infinitesimal laboratory experiments and the colossal demands of full-scale production. It pioneered techniques previously confined to the realm of speculative fiction: remote hot cell operation, where unseen hands manipulated deadly materials behind thick walls; sophisticated chemical staging, orchestrating complex reactions across vast distances; impenetrable shielding, safeguarding human life from invisible threats, and precise process control, ensuring stability in a volatile environment. All these disparate elements were fused into one audacious functioning system. Its prodigious output directly fueled the subsequent wartime milestones, accelerating the dawn of a new, terrifying age. Yet, the deeper engineering lesson it offered extended far beyond the immediate exigencies of conflict. The T-plant unequivocally demonstrated that when stakes are impossibly high and uncertainty looms as an omnipresent shadow, the winning design is often the one that offers the most unwavering control, not the one that appears most elegant on paper. That profound lesson resonates with undiminished power even today. Modern nuclear operations, from power generation to waste management, still rely heavily on the principles pioneered at the T-plant: remote handling, meticulous shielding, stringent contamination control, and the indispensable hot cells. Process choices continue to be dictated as much by the practicalities of maintenance and repair capabilities as by raw, theoretical efficiency. Across a spectrum of critical industries, from the labyrinthine complexities of chemical plants to the microscopic precision of semiconductor fabrication, from the intricate choreography of pharmaceutical manufacturing to the audacious frontiers of space systems, engineers perpetually confront versions of the very same question that loomed over the T-plant in 1944. Do you commit to the process that promises optimal performance under ideal, pristine conditions? Or do you choose the method, perhaps less refined, that demonstrably continues to function, continues to deliver, even when maintenance becomes a Herculean task, access is severely restricted, and the cost of failure is utterly catastrophic? The T-plant's answer, etched in concrete and steel, was unequivocal. Choose the method robust enough to survive the brutal crucible of reality. And this, precisely, is why bismuth phosphate mattered so profoundly. It was not merely a chemical reagent, a formula in a textbook. It was an engineering compromise, a pragmatic concession, transformed through sheer will and ingenuity into a fully operational production system. It was a solution purpose-built for a giant concrete canyon, for the unseen hands of remote controls, for the silent, pervasive threat of radiation, for the breakneck speed of wartime urgency, and for the uncomfortable, inescapable truth that even the most perfect methods are utterly useless if the plant, when the world demands it most, cannot keep running. A common narrative reduces the monumental effort at Hanford's T-plant to mere chemistry, but on the night of December 26, 1944, inside those concrete walls, a far more profound drama unfolded. This was the heart of the Manhattan Project's industrial might, the world's first full-scale plutonium separation facility, handling materials of unimaginable toxicity and radioactivity. Engineers were not simply mixing compounds. They were orchestrating a ballet of dangerous elements, devising intricate systems to control reactions from behind thick shielding. They grappled with an almost impossible logistics and process control problem, inventing solutions in real time with the tools they possessed, not the ones they dreamed of. Every valve turn, every calculation, every decision carried the weight of a global conflict, pushing the boundaries of what humanity believed achievable. The silent triumph of that night was not merely a scientific achievement. It was a testament to the relentless human spirit, forging the best workable answers under unthinkable pressure.